So we can start with Richard on adversarial patches for aircraft camouflage. Richard, are you here?
Yes, I'm here.
So the floor is yours. So I don't know if you have slides or you want just to.
I've not prepared any slides, but I'll just give a short introduction.
Yeah. That's perfect.
So we've been interested in applying adversarial AI for a specific application, which is aerial surveillance. And in aerial surveillance, you typically have a lot of data that's being recorded, and it's very interesting use case for automatic image analysis, say automatic object detection. And we were interested if a recent approach proposed by University of Leuven that proposed adversarial patches for camouflage, if that was usable in an aerial surveillance scenario. So building on this method, we tried several configurations of camouflaging objects in aerial images. And we found that it can be quite successful even if the patches are relatively small, which was kind of a surprise to us as well. And we did experiments for one network, for the YOLO network. We also acknowledged that it's most interesting also for this use case to test this over the board across different types of networks, because you never know a priori which type of network will be used for detection. So, but this is for future work. So in short, this was my intro. I think I've passed 1 minute by now.
Oh, that's perfect. Thank you. So I've pre-selected 2 questions for each of you. Maybe if you have more time, we will come with more questions. So the first one is from Catherine Gross, which found that colorful patches was really interesting to be so successful. So her question is, do you have any intuition if colorful patches is related to the encoding or some parts of the model?
The detector model that we used to trick was trained on color data. That's one. So color has an effect, but the reason that it's so very bright in terms of colors, our intuition is that it has something to do with the extreme values of the color space. So that the more extreme the values are, the better a small patch can trigger the model and trigger it into obscuring the object and removing the detection. So because the patch is small, we think the pixel value should be quite extreme, and therefore we get very bright and saturated colors. That's our intuition.
Okay, thank you. The second question is from Mark Muller. And this question is there any data on how well the applied object recognition methods function against more traditional camouflage? So
it's a very interesting question. We have not experimented with that ourselves, and nor did we do a lot of literature research on that before we started with this work. But we suspect that traditional camouflage can be quite effective, also for trained detection models, but we're not sure if the level of effectiveness is the same as for manual detection. So that's still a question. So we can only speculate that it will probably be effective, but we're not sure if, for example, models can be trained in such a way that they will try to focus more on the outline of objects, for example, in such a way that they're still able to discern silhouettes of vehicles or other objects in order to recognize them. So it's something that probably should really experiment with, especially in the field of deep neural networks, to see how effective that is.
Okay, thank you. We still got a little bit of time, so I have time for my question. I'm really happy about that. So I hope it's not something I missed in your presentation, but I was really curious if the adversarial patches you got are robust to some spatial adversarial attacks like zooming or brightness changes, and also if they are transferable to other aircrafts or drones.
Yeah, the patches are robust against small variations. So before we place the patches in the images, we apply some small contrast changes. We add some noise. We change the orientation of the patch a bit, just to mimic real-life recording conditions to some degree. We have used them on different sized objects in the images, from small to larger planes in the paper, and also different types of planes. So overall, they are robust, or they work for different types of objects, scales, and also are robust to some degree to typical recording fluctuations. Yes.
Okay, thank you. I think yes, I will try to be fast so we can have David Stutz's question. Camouflage is obviously a topic highly relevant in military or defense application, but do you have any non-military situation where it could be of usefulness?
An interesting approach that we found in literature was an approach where face recognition system was kind of fooled by not really camouflage, but like a crafted adversarial attack. So that's kind of in the security domain, and we suspect in the security domain you may have some applications. For example, also camouflaging persons for a security camera can be an application. I'm not sure how realistic this is, but I guess that in the security domain there will be some possible applications, but definitely most logical ones are in the defense domain.
Okay, thank you. So we're done with Richard, but if you have any more questions or if you wanted to add more to your questions, do not hesitate to meet in the coffee room after.
Okay, yeah, so the talk I've been recording, let me switch. Yeah, so the talk I've been recording is related to holistic adversarial robustness. So we know there are many experts in this workshop, but and we most of us focus on one particular type of adversarial threat, right? But if you look holistically, and you look at how these AI models are being developed, there are ways you collect data, you select your model, and then how you deploy your model. And in each step, there is a way for adversaries to go in and manipulate our system. So really, depending on what are the attacker's objective and what the capability they have and what knowledge they know about our system, we can map this attack to different scenarios. And so this is kind of one way of a holistic view I want to show. And the other holistic way, I mean by holistic way is, I would argue like future effective robustness testing and evaluation should be made model agnostic. It should be independent of the details of the model, but rather treating the machine learning model as a truly black box. But you still want to make it safe and verifiable. On the other hand, we are still using data as the much knowledge as we can to use domain-specific knowledge and data to make our system robust. And all these techniques have to be made practical. That means that we care about efficiency, utility, and compatibility, and so on. And with that in mind, we have a good vertical mapping between different terminologies to this a series or a pipeline of procedures to test our adversarial robustness, right? Including attack will be mapped to bug finding, defenses will be mapping to model hardening, and verification will be mapped to certificates you give to a model or system. And there are also the aspect of what are the new applications to the original AI problems once we know better about the robustness of the model. So feel free to go to my video for more details. Thank you.
Thank you, great, Pinu. So I will dig into your questions. The first one is from Maxime. So I will summarize it. Sorry, I forgot where. If we're interested in being robust to small infinity perturbation, it's usually unclear what is the right infinity radius, what we really want to be robust in. Of course, this aspect is very application dependent, but Maxime would like to hear your thought on your experience with practical deployment of robust models. So basically how to pick the radius, for example.
Yeah. This is a great example. So we always have the difficulty of choosing the right threat model, right? In this case, the perturbation bounds to evaluate our robustness. And this threat model will vary from task to task and also vary from data modality to data modality. So for images, it makes sense to talk about an infinity attack. For text, it makes less sense to do so. But eventually, I think we should. One analogy I often make is when we are buying products that feature waterproof, right? It's not like infinitely waterproofable, right? There's a limit. So for example, if you go buy your watch, it will say, okay, it's waterproof up to 100 meters. So I think we should really build this notion to our model users and end users that when we are talking about safety and robustness of a model, there is also a limit they should have in mind, right? So we can say, okay, I'm offering you a model that is infinity robust up to a certain degrees, not like infinite robust. I don't believe such infinite robust model exists. So I think part of the reason we have this workshop is also we want to educate and broadcast this message and the robustness notion to the users so they can set the expectation right, and then we can make our lives easier.
Thank you. The second question is shared with mine and Giant, so we hope it's not a silly question. It's just that we were really interested in your clever score and would like to hear more about the intuition behind.
Yeah, so that's one. You have a very good taste, first of all, and this is one project.
I think you're biased.
We really like about, right? So when we invented this score, we are saying, hey, how come people are using different attacks to evaluate robustness, and you never know how good or how bad these scores are, right? Because there is always a better attack, and it is true. Afterwards, you see more advanced attack and breaking defenses and so on, right? So. But to make the model universal and make the robustness evaluation compatible across different the whole spectrum of models, we really need a unified score, and that's what motivates us to propose this clever score. And the other thing is that clever score is one of the typical example I mentioned to be model agnostic, right? So we want a score that is very efficient to compute and does not rely on the model structure too much. Right, so we know a lot of certification methods, they can provide certified amounts, but they have to propagate these errors layer by layer, and that propagation nature prevents this robustness score to be scalable and efficiently computable, right? And this score will manage as the network go deeper. So so we are very happy about the clever score, although it is not a truly certified bound, but it actually approximates the minimum distance to the closest decision boundary pretty well, and this notion of margin, I think, is a very useful in practice, and we have seen the gap between that clever score to the actual upper bounds, the empirical robustness is very close. So we are very happy about the score.
So I gave a talk on the difficulty of the hardness of adversarial machine learning, where I go a little bit beyond the typical arms race, which I think we all know by now. And I mainly made 3 points. The first one is the importance of the knowledge of the user of machine learning. And the example I gave was an attack which we introduced, which is called adversarial initialization, where you tamper with the initial weights and then the resulting network obtains a little bit worse accuracy. The second one is the interaction of different attacks, and this is something that goes into the direction what you just mentioned, like the holistic picture. So what we show is like if you have a classifier, you can maybe make it robust towards one attack, or maybe more robust towards one attack. But then it might actually be more vulnerable towards another attack. So we should not study attacks in isolation. And then the third point was the difficulty of formalizing these problems. And I gave the example here of a measure that can detect a backdoor that was introduced maliciously during training. However, you can also use this measure to prove a benignly occurring pattern in the network. So it's really the intention that makes a difference here. And this is, I think, a huge problem if you try to define what is security here.
Thank you, Catherine. So here's your 2 questions. The first one is from David Stutz. Your approach assumes that the pattern for detection is known. Question. And does it also work for less perceivable patterns then, such as adversarial examples?
Yes, so that we assume the pattern is known is correct. You could technically use approaches to generate that pattern, but then you run into the problem that I just described. So you can generate a pattern that is detected by the measure, but that is not occurring as a vector in the model. Concerning the visibility of the pattern, so what we found is that the only requirement for a pattern to be detected is that it causes a really stable classification of the inputs where you apply it to. And as far as we know, but we haven't really tested this through and through, is that this is not related to the size or the perceptibility of the trigger. But you could think about designing one that might fool the measure, as I said before.
Okay, thank you. The second one is from Dennis Mazzucato. So do you think that the poisoning technique could be encoded also as form of robustness?
Yeah, so I mean, like this approach that we've done here is purely empirical, but it would be great if we could formalize that. Personally, giving my work that relates to GNN training, I've seen that they are really, really random and very that they change quickly. So if you change something in the training, it would just like readjust and then go ahead. So I think this could be really hard. It would be great if we could. But yeah, I don't really see any concrete steps there, to be honest, right now.
I feel Dennis got maybe some ideas, so do not hesitate to exchange on this.
Yeah, he's free to come over. I would be curious if he has some ideas.
Great. So thank you, Catherine. Jayan, do we have more time?
Yeah, we have a bit more time, and then we move on to needs, but we can ask one more question if you want.
Yes, okay. So one common question we got with Giants, it was if you have concrete examples of the adversarial attacks you had for the initialization of the network.
Okay. Yeah, so like the attack that we foresaw there was that you have 2 competitors out in the wild and they are competing for a certain product and they're both collecting data, for example, to build their products. So you have a data set where you don't know the accuracy that you can achieve. And then one way to like discourage your competitor from making their product would be to either hack their machines directly and replace the library, or maybe just cause a drive-by download and then alter the library, because what we found online when we searched forums was that people don't necessarily gradient check their implementations. So they are unlikely to find this cause if you tamper it with a library.
Okay, thank you.
Yeah, thanks for having me in this workshop. I enjoyed this very much. So what I did present in my talk were several approaches to what I would call AI robustness or AI dependability, and I work on planning scenarios that suffer from uncertainty and partial information, partial observability. And I presented first our general approach of including learning with verification in a sense to have outcomes of learning or decision making a bit more reliable, to give some measure on the reliability of AI decision making. And I showed approaches that used for specific model called partially observable market decision processes, POMDPs, how we could connect them with learning for recurrent neural networks. And this was what the result we had, where we included verification to the learning of RNNs for these POMDPs, and we could solve problems with millions of states, which was rather unrealistic before. In a continuation of this work, we used so-called finite state controllers to extract them from these recurrent neural networks and apply them to PomniPs. And there was a question about that. I will answer it later. And then I moved on to some results where we kind of dropped the assumption that in these models, these formal models that you have, that there are point estimates of probabilities possible. Like, I don't know, a pedestrian will cross the street with probability 0.99 or something. We rather made these ranges, so to a bit account for statistical uncertainty. Yeah, and I showed a lot of examples that we use. We have a lot of applications that we try to embed in this research. And yeah, I guess that's it. I'm happy to answer the questions.
Thank you, Niels. So the first question is from Juan Zhang. So Juan asked, the example shown in this talk is a simple green environment. So in practice,
we're interested in validating controllers and decision-making systems in cyber physical systems, especially when the controller is represented as a neural network. So my talk mentioned two different kinds of approaches. The first one is sampling-based methods, and I spoke about the adaptive stress testing, which basically frames the problem of finding the most likely failure situation as a reinforcement learning problem. And then we can use a bunch of off-the-shelf reinforcement learning algorithms to find that most likely failure situation. And this was used for the validation of ACAS-X and other systems. It seems to be scalable. And then the second category are formal methods, and of course we'll be talking about formal methods tomorrow. So an example of that is the ReLUplex algorithm that Guy Katz led the development on. But the end of my talk focused on the merging of these two different kinds of approaches to find really, really interesting failure conditions that wouldn't have been found using either one of those methods on their own. And the application that we explored was the TaxiNet example. So we had this X-plane simulator. The input was a continuous video stream of from a camera mounted on the side of an aircraft, and the controller tried to keep the aircraft on the runway center line. And by combining these two different methods together, we were able to find a very interesting sequence of image perturbations that would actually drive the aircraft off the side of the runway.
Thank you, Michael. So the two questions is, the first one is a more practical question from Catherine, which asks how long does it take to run your simulation and how adaptive are they? So if she has a similar task, she was talking about navigating robots in a car factory. Could you simply use your procedure, and how much time would it need to set it up?
If she's referring to the simulation that we showed at the end with TaxiNet, that was about, it was a little slower than real time. And so this is the very first research that we did on this line. And the network that we were exploring only had, it was a relatively small network. So I think we're pretty far from being able to do this in real time with a large perceptual network that involves like image recognition and so forth. And yeah, that would probably not be practical right now. But the concept is super interesting. And as advances are being made in formal methods, which we'll talk about tomorrow, then hopefully this will scale up. The other thing that we can do is explore. So for the TaxiNet example, we were using ReLUplex and ReLUval, or Marabou, the newer version of ReLUplex, and those are sound and complete methods. We may be able to compromise on that and come up with something a bit more scalable.
Thank you. So it's perfect for the second question from Huan Zhang. So when verifying your network controller, you used reachable analysis to predict the possible actions and then move to the environment or possible next states. When the system dynamics is more complicated, or when the trajectory is very long, the number of states can be quite large. So do you have any thoughts on how to scale reachable analysis to that setting? I'm really curious about that.
Yeah. So the middle part of my talk summarized what we did for reachability for aircraft collision avoidance, and for that, you might recall we had to discretize the state space into a bunch of cells. And of course, anytime you go about discretizing something, you have that potential cursive dimensionality. There's another challenge here, where, as was mentioned in the question, when you have very long sequences. So the approach that was taken in this presentation is at each step we concretize the states that are reachable at the next step, right? So we looked at all of the cells that are reachable at the next step, and we chained those together. And of course, as your time horizon becomes long, the possible reachable space becomes super big. So one of my other students, Chelsea Sidrain, and I spoke about this at the IJCAI keynote yesterday. The approach she's taking is to not do this concretization at every step, but rather she takes a symbolic reachability approach, which doesn't require this discretization. It provides much tighter bounds, but since we're solving over a longer time horizon, it makes the problem become a lot larger. So there are trade-offs to be explored there. For her formulation, she used a mixed integer programming formulation, and that MIP problem becomes a bit larger.
Okay, thank you. Very interesting.
Thanks again for having me. So in my talk, I talked about two recent projects related to robustness, both kind of empirical robustness. The first one, a variant of adversarial training called confidence-calibrated adversarial training, where we try to obtain robustness against different types of adversarial examples. And we do this by biasing the model towards kind of low confidence predictions on adversarial examples that we see during training. And then at test time, we can reject those adversarial examples, and this way we kind of generalize robustness to different types of attacks that we haven't seen during training. So this was the first part, and then in the second part, I looked a bit on robustness in weight space, which is, there's not a lot of work on that, and we have a very kind of nice application in mind, specifically in chip design or in kind of deploying neural networks on actual chips. We try to save as much energy as possible, and it turns out that with kind of all these deep networks, kind of the memory consumption or the energy consumption due to memory excess is kind of the most significant part. And we can kind of reduce this by operating the chip at lower voltage, but this comes at the cost of kind of bit errors when reading and writing. And we show that if we can train networks that are kind of robust to kind of these bit errors in their kind of quantized weights, then that we can basically keep the accuracy more or less untouched while kind of reducing voltage and energy. So this is kind of two slightly different angles on robustness.
Indeed, this is really interesting. Thank you. I really appreciate your presentation, by the way.
Yeah.
So, oh, it's fine. I've got two questions for you. So, could you give an intuition on how much energy you could save this way?
Yeah, so this is actually hard to answer in general because it strongly depends on which architecture you're talking about, which chip you are talking about. So actually translating a neural network to a chip, kind of coming up with the optimal data flow is actually non-trivial. So what we did is we kind of oriented ourselves at a recent chip that was proposed that was also in the realm of low voltage operation called Dante. And they have kind of data, and we basically used the data to come up with kind of the bit error rates that we studied. And as the bit error rate kind of increases exponentially when lowering the voltage, we already can get a significant gain kind of without increasing the bit error rate too much. So in our case, just as an example, on Cypher 10, we had a test error of around 4.3%. And with kind of a bit error rate of 0.1% across all bit errors with kind of an 8-bit quantization of weights, the test error increased slightly by, I think, not even 1% to 5 point something. And we already would save like roughly 20% of energy, right? So this is constrained to kind of the energy for a memory excess, but as kind of this is kind of the most significant part compared to computation, this might actually translate to quite significant ones. And then another example would be with 0.5% bit error rate, we would have 30% energy savings, and the test error increased slightly more. And then, of course, we can combine this with kind of low bit quantization. So if we go down, for example, from 8-bit to 4-bit, this naturally translates to kind of halving the energy consumption because we kind of need to read and write less bits, obviously. Yeah, but that's a good point.
Thank you, David. We'll go briefly with the question of Mark. Have you experimented larger perturbation during training to include larger regions of high confidence while maintaining the generalization to low confidence?
That's a good question. So we didn't experiment too much with larger epsilon balls. One reason is obviously that we want to be comparable to related work, and kind of the epsilon balls that we used are sort of standard. The second point is that there's also kind of a discussion of whether larger epsilon balls actually make sense, right? So there are papers arguing that if we increase the epsilon balls kind of a bit more, then we already have examples in our epsilon ball that have different labels. And then the whole idea of being kind of robust within this epsilon ball is a bit fragile. To the second point regarding having kind of a larger area around the example where we still predict high confidence, that's something we also tried, considering a different transition. So right now we have a very steep transition from kind of high confidence to uniform confidence within this epsilon ball. And we also tried a different transition, which allows us to kind of interpolate between regular adversarial training and confidence-calibrated adversarial training, meaning we transition slower and we have kind of a larger region in the middle where we have high confidence. And so experiments basically showed that when you interpolate between these two behaviors, you also interpolate between the strength and the weaknesses. So if you want to have an adversarial training-like behavior, you are stronger on the adversarial examples you see during training, but you are weaker, you generalize less well to new adversarial examples. And if you kind of are more on the side of our confidence-calibrated adversarial training, you are usually slightly worse on the adversarial examples you have seen during training, but you generalize way better, right? So there is a trade-off there.
Thank you, David. We'll have to stop for the question.
My work is on robust reinforcement learning against adversarial perturbations on city observations. So the settings we considered are the deep learning-based agent, which observe the environmental states through some observations like sensors, and we attacker or the sensor noise can actually change the environmental states. So the observed states can be different from the true states. So we first formulate this setting as a state adversarial Markov decision process and study the worst case adversarial perturbation on state observations. So in the SAMDP, we have an adversary before the state input of the agent, and we can perturb the agent to perturb the state to another state defined by some perturbation set. So we have two approaches to solve the SAMDP. We found that solving it optimally is very hard, so we have two indirect approach. The first one is trying to find a policy that is insensitive to state perturbations. Like if we have two states very close to each other, we also want the actions to be close to each other. The second approach is more like adversarial training in classification problems. So we first fix the policy and find the optimal adversary, and then find the optimal policy under the fixed adversary. So the two problems are becoming solving an MDP or a POM-DP problem, and we can alternate the two steps above. And the interesting finding is that by using this formulation, we can actually define the optimal adversarial attack, and under this optimal adversarial attack, we can actually find a significantly stronger attack that makes the agent not just make the agent fail, but make the agent move into the opposite direction. So finally, we show our algorithms on three types of algorithms: PPO, DDPG, and also DQN, and they work very well. So that's my presentation.
Thank you, Juan. So your two questions. The first one is from Giant. Giant is curious about the training time of your models. If you have more details, what is the price to pay to learn your most complex policy compared to other methods you compare with?
So like for the training time, I think we have two approaches. The first approach is to regularize the policy such that the policy is insensitive to state perturbations. If we take this approach, then we just need an additional regularization term during the policy training process. So the additional regularization term can be solved using projective gradient descent. So it's like you have to pay like 2 or 3 times more cost depending on the number of PGD steps you used. The second approach is on like alternating the training of a optimal adversary and the agent. That one is more tricky because you have to train the two things together, and it's sort of like a GAN training. So you have two agents are competing with each other, and it's harder to converge. And in that setting, you probably need maybe 10 times more computational cost to train a robust model. And so what we found in our paper is we can combine the two approaches together to achieve the most robust agent under a strong suite of white box attacks. And but you have to pay maybe 20 times more cost for that. I think that is actually comparable to adversarial training. Like when the adversarial training was just developed, it was also quite slow to train a robust model. And of course, people are keeping improving adversarial training. And for reinforcement learning, this is just our like first work. So we still have a large room for improvement on the time complexity part.
I'm confident you will still improve. What you already do is really good. So thank you, Huang. And the second question is from Niels Jensen. So he found your work also as well very interesting. As for your model as PRMDP with memory-based policies, or your approach on finite memory policies should work. Oh, sorry, I was reading at the same time. So he thinks that his approach on finite memory policies should work very well. So you should definitely talk with each other.
Oh, sure.
So it's all for the question.
So Adam was there, but he left. I just would like also to really thank Adam, even if he's not there. I know that Nicola is there. Maybe he can transfer the great thank you for the real good work, great work that was done for the review, very comprehensive review.
Yes.
So I hope that he will be able to connect to share his knowledge. But a really big thank you to Adam for the great review.
Oh, thank you so much for the kind feedback.
Sorry?
I'll let him know.
Okay.
Thank you.
Yeah, he probably had to run back because he's cramming on some ICML submissions.
Okay.
Oh yes. So good luck for him.
Okay.
Thank you.